Maybe you hated math in school. So did I. But you know, there's hope in those numbers, even if you don't understand them. I have very logical reasons for believing in things that logic and reason could never teach me. It's kind of ironic, but the more complexity science finds in life, the less likely becomes the whole scenario in theory they use to explain its origin. The really amazing thing is that quantum physics shows that nature, at its most fundamental level, strains human credulity and knowledge in ways biblical faith never does. Hi, Cliff Goldstein here. Welcome to the program. The name of this program is called The Unreasonable Effectiveness of Mathematics in Natural Science. And it's based on a famous article written by Eugene Wigner in 1960 called, well, The Unreasonable Effectiveness of Mathematics in Natural Science. And the article was about, well, yes, the unreasonable effectiveness of mathematics in natural sciences. Now, what am I talking about here and why? Well, Wigner was a physicist, and though well-known, publishing a lot of technical works, and eventually he won a Nobel Prize, he wrote this famous article. Probably that's the one thing he's more known about than anything else he's done. And in it, he considered a question about how science works in the natural world. And he quoted it in a publication called Communications in Pure and Applied Mathematics, Volume 13, Number 1, February 1960. Yeah, sounds like a real nail-biter, doesn't it? But anyway, what was he talking about? Well, he told a story about a guy who was a statistician who was talking about population trends. And he showed a friend this fancy paper with all these complicated symbols on it. And at one point, one of the friend was a little incredulous about all this. He pointed to one of the symbols and said, "What's that symbol?" And he said, it's pi. It's the ratio of a diameter of a circle to its circumference. And the friend looked at him and said, "Well, now I know you're pushing your joke too far, because surely the population has nothing to do with the circumference of a circle." Well, the point is it does. It does have something to do with it. In fact, it has a lot to do with it. And he used this to introduce something that he talked about, the mysterious link between numbers and the physical world. And he says there's no rational explanation for why numbers work so well with the physical sciences. Now, it's kind of strange if you think about it. I mean, what's more rational than numbers? Okay, what's more rational, and that for natural science too is what you would think is rational. And yet, in the paper, he talked about the mysterious link between them. Mysterious? That's generally not a word you think about for mathematics. You know, we're not talking parapsychology or about the occult. I mean, we're talking about numbers, math, 2 + 2 = 4, and the like. But you know, it is a little weird if you think about it. You got a scientific paper dealing with population trends, and in it, he uses the symbol for pi, a symbol from geometry, in talking about population trends. I mean, if he was studying circles or bubbles or the like, that would be fine. But population trends? And so the question is, what does one have to do with the other? And yet the fact is we use mathematics, or scientists use mathematics all the time. And it's so common, we rarely, we don't even think about it. And yet it's really quite strange. And that's what I want to look at. If you've ever studied science, maybe even high school science, you'll know off the bat how central numbers are to it all. I mean, look at a physics book. I mean, before you flip 2 pages past the table of contents, what is it? It's math, 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 all the way through, pretty much till you get to the inside back cover. I mean, when they talk about protons or neutrons or quantum fields, if you look at it, they're using what? Numbers, numbers, numbers. Have you ever looked at some of the math that's involved in quantum physics? Man, the fact is you need years and years and years of complicated math to be able to do the math that they use in studying nature at its most fundamental level. Or an astronomy textbook. When I was young, I used to think I wanted to be an astronomer. I thought I'd sit there, look through a telescope, and philosophize and muse about Pluto. If you open up an astronomy textbook, it's math, 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 fluid dynamics, math, 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 all the way through, from the world of the super small, the quantum realm, to the super large, the study of galaxies. Guess what? Math is used to describe it. But again, we're so used to it, it really is kind of strange. I mean, how could you take something that, well, something that humans created? I mean, what, did calculus just fall out of the sky? No, humans created it. Humans create this stuff, and it works so well with understanding the natural world. How can that be? And you know, see, we're not really using numbers like you build a rocket ship and you build the math into the rocket itself. We're not talking just that. I mean, of course, you know, because really, it takes an awful lot of math. It takes an awful lot of math to fly a rocket, to fly a plane even. And they build that math into the project itself. But what I'm not talking about that per se. I'm talking about looking at something in the natural world and then suddenly discovering the best way to explain it or to describe it is to use something that we created, mathematics. You know, we've all heard the story of Isaac Newton and the law of gravity and the apple falling on his head and all that. Well, in 1687, Newton published his famous work, and it was called the Philosophia Naturalis Principia Mathematica. This was the work in which he formulated the law of gravity. Okay? Well, let me not too hard to translate it for you. The mathematical principles of natural philosophy. Natural philosophy was the word they used back then for science. But again, Newton was looking at the motions of the planets and the stars and the earth and the sun. He's looking at all that, and he has to use mathematics, numbers. He has to tack them on, so to speak, to explain it. If you ever look through the Principia, it's numbers, 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 geometry all the way through. So all over the world, so all over the natural world, scientists use, from the subatomic world to everything, they use mathematics to describe what is going on. Notice, too, I use the word describe. This is, I could do a whole show on this. Describing something is radically different than explaining it. Newton, in his Principia, described what the planets did. He didn't explain anything. In fact, he said he had no idea whatsoever why the planets did what it did. And you know, today we got all this fancy scientific equipment, and we can look and we can parse and we can probe and we can do all this, but really in the end, all they end up doing is describing the natural world. They have a hard time explaining it. I mean, everybody knows the most famous E equals MC squared. Everybody knows that. But you know, it explains absolutely nothing. All it does is describe. But either way, explanation, description, my point is, how is it that mathematics so accurately, even mysteriously, as Wigner called it, worked so well in the natural world? You know, this is nothing new. 500 years before Christ even, 500 years before Christ, a man named Pythagoras, he gave almost quasi-mystical status to numbers. He even started like a little religious cult, a religious sect around numbers. And it was all built, he believed all reality was made of numbers, whole numbers. And they built a whole religion around it. But then they had a slight problem one day. Somebody discovered irrational numbers, something like the square root of 2, which isn't a whole number. And oh, that was heresy. I mean, that pretty much did their theology. And so they swore all the members to secrecy. And one poor schnook got caught telling people, and the rumor was, or the legend has it, they took him out and drowned him. Clearly, Pythagoras was somebody who took his numbers seriously. But the point is, here was a man 500 years before Christ, 500 years before Christ, who saw the powerful relationship between the natural world and numbers. You jump ahead 2,500 years later, there's a physicist today named Max Tegmark. Max Tegmark, and he argues something similar. He's arguing that at the bottom level, all reality is at the core mathematical principles. And Pythagoras even noticed, a little less metaphysical, that music, he noticed a whole number ratio between octaves and certain tones in music, and was able to use mathematics to explain music, as well as he pointed up to the stars and looked, he saw mathematical things in the universe as well. He was the one that coined the phrase, I believe, the music of the spheres. And centuries later, you look at the work of Copernicus, Kepler, we saw Newton, all used mathematics to explain, I got caught. They don't explain, to describe the motion of the planets. They didn't come to an explanation till Einstein, and even that's not a total explanation. But anyway, as I said, the bottom line of all of this stuff is it comes to math. In fact, outside of Plato's Academy, a few centuries after Pythagoras, he had the words supposedly on it, said, "Let no one enter here who does not do geometry." I mean, they did more than geometry in Plato's Academy, but that's how basic and fundamental he believed math was. A few centuries later, there was a mathematician named Aristophanes who did a few simple measurements, and using math a few hundred years before Christ, using the math, he pretty much was able to give us the basic circumference of the earth. It was amazingly close, and he did it through mathematics. And then, of course, we've all studied Euclid. If you had any high school geometry, you had Euclidean geometry. For 2,300 years, this geometry was considered the most perfect explanation for reality, and was even considered the foundation for how we thought. I remember the 9th grade geometry, Mrs. Brenny's teaching us that, well, you study geometry, you'll learn how to be more logical and rational in your thinking. And she was talking Euclidean geometry. Anyway, math was used to describe everything scientifically. In the 1600s, Galileo argued that this is interesting, he said, mathematics is the language of nature. Okay? But again, I asked this question. Why should numbers, math, something that we don't even know really exists, that's a whole other talk here. I think I did a show on that years ago. But why should numbers, math, so accurately describe the world we see out there? How do numbers fit in with something as complicated and erratic as nature itself? Now, here's something fascinating. In the 1800s, independent of each other, there were these math geeks, and they sat around doing non-Euclidean geometry. Okay? That is, they were using a whole different set of axioms and postulates and theorems than Euclid did. Euclid started out with these few axioms and postulates. They started out with different ones. And you know what happened? They ended up coming up with a perfect geometry. It worked perfectly. It was just as consistent and worked just as well as Euclid's geometry. That it was just as logical, just as rational, but Euclid did everything on a smooth plane. They did the geometry like on a curve in different shapes. And the point is, it worked beautifully well. The only problem was, it was completely different from the geometry of Euclid. You know, in this geometry, you know, remember Euclid, parallel lines never meet. We all learned that. In this geometry, parallel lines did meet. And remember, we're always taught the angles of a triangle are what? They're 180 degrees. Everybody knows that. In this geometry, the angles of the triangle, depending, were more than 180 degrees or less than 180 degrees, all depending on the kind of geometry that they did. And everybody knows the shortest distance between 2 points is a straight line. Everybody knew that for 2,300 years. Everybody knew that. In this geometry, the shortest distance between 2 points was not a straight line. Anyway, the point is, these geeks sit around, they come up with this stuff, and everybody thought, okay, fine. This is a nice thought experiment. I'm glad you guys got the time to sit around and conjure this make-believe stuff that works. That's fine, but it doesn't. It's got nothing to do with anything. Okay. Well, jump ahead 50 years. Albert Einstein comes up with his famous theory of relativity, general relativity. He came up with special first, general came later, and I mean, I could even do the math for special relativity. That's simple, but Einstein couldn't even do the math for general relativity. He couldn't do it. He couldn't make it work. And then somebody appointed him to this non-Euclidean geometry that these guys concocted in their heads 50 years earlier. And amazingly enough, guess what? This non-Euclidean geometry worked. This geometry explained how gravity worked, how mass bent space and times. In other words, it was actually more true of the real world than Euclidean geometry had been, that had reigned for 2,300 years. Now, this might seem like a bunch of esoteric stuff. What does it all mean? But here's the point. Here's the point. Some bunch of math, a bunch of egghead math geeks sit around on their computer or their slide rule or whatever, and they play with numbers just for the fun of it. Just for the fun of it, you know, purely theoretical and the like. And the next thing you know, suddenly they discover this math. Somebody years later studying animals or studying conch shells or studying the formation of the stars, they think this math that these people made up in their heads, this describes the stuff perfectly. That's what happened with the non-Euclidean geometry. These guys composed this stuff, made this stuff that doesn't mean anything. 50 years later, Einstein comes along and says, wow, this describes the geometry of space-time purposely. And it's not just this. Things like Things like the pattern of flowers or complicated knots, spots on leopard skins, the spiral of a conch shell. All these things, people had done the math before, just for the fun of it. And the next thing you know, it fits perfectly the real world. I'll tell you a fascinating example of this was in the early 20s. There was this physicist named Paul Dirac, and he posited the existence of something called antimatter. Later it was called positrons. He did it purely by math. He didn't do any experiments. He just did this math, and he said, there's got to be antimatter out there. Well, what do you know? In 1932, a positron, the antimatter particle that his mathematics predicted, was discovered. So here's a guy sitting in an office with a piece of paper and a pencil, and he, using math, and predicts the antimatter. We've all heard the story about the Higgs boson. Well, years before the Higgs boson, this guy Higgs, without experimental evidence, just using math, predicted this Higgs boson would exist. So what do? They build this giant CERN particle accelerator. They spend billions of dollars, in this giant atom smasher in Europe. They smash these protons together. All this stuff comes out. They have layers and layers of computers to analyze it. Boom, 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 boom. And then eventually, boom, they get a bump on the screen. They discovered the Higgs boson experimentally. But this guy, Peter Higgs, decades earlier, just doing math, said it's going to be there. And sure enough, years later, it turns out to be there. How does that work? How does that happen? Clearly, I'll give you one other example. It was so funny. Again, it's Einstein. Einstein's visiting Hubble, Edwin Hubble, with the Hubble telescope, or I guess I don't know what they called it. They named the Hubble telescope after him. He was the one that first pointed to the universe expanding. And they're walking through with their wives, and Hubble's wife is saying, pointing to the telescope and so on and all that he did. And Einstein's wife says, my husband figured all that out on the back of an envelope. Okay. Now, whether that's true or not, I don't know. But the point is, it might have been. Einstein worked it out in his head. In fact, Einstein worked out that the universe had to be expanding. His math and general relativity told him that. He didn't like it. At the time, it didn't make sense. And then what do you know? They discover the universe is expanding. Again, the question, how do you find this powerful connection between mathematics and nature? I mean, it's there. It's there. You can't deny it. But the question is, why? Why does it work so well? Years ago, a British physicist, a Brit, they're not exactly the most religious people in the world, he says, the universe appears to have been designed by a pure mathematician. What do you know? The universe appears to have been designed by a pure mathematician. A while back, I read a book called Is God a Mathematician? And I guess the point is, maybe these guys are atheists, whatever they are. They're looking out and they're seeing all this precision, all this mathematical stuff in the universe, and they're coming to the logical conclusion that, this just wasn't happenstance. This seems to be planned. In other words, it seems like mathematics works so well because that's how God created. A logical mind created the world in a logical way. He created it in such an orderly way that mathematics itself helps uncover what that order is. Math is so orderly, and how amazing that it helps explain the orderliness of nature as well. Years ago, The Greeks, the ancient Greeks, which were doing this a long time ago, the best that they could, they talked about the logos, which can be understood as kind of a divine reason or divine order in the natural world. I mean, even amid the chaos, even amid floods and earthquakes and famines and disease and war and the uncertainty, they were still able to detect a kind of rationality, a kind of order to reality. And again, this was millennia ago. Well, over the millennia since then, mathematics has been and has still been able to help show us how much order is out there. You know, if you want to think, so many of us have been programmed to think about everything happened purely by chance. You know, if you want to believe that it's all by chance and happenstance, and, you know, I guess you could always find enough reasons to believe that if you want. Go ahead, if you're inclined that way. But it's interesting, even Wigner, and I have no idea what his religion is, if he was religious at all. I didn't get that impression. In that famous essay on the unreasonable effectiveness of mathematics and the natural sciences. Unreasonable. It's unreasonable if you don't believe in God. If you believe in God, if you believe in the Logos, in the beginning, you know, the Logos, Jesus, then it makes perfect sense. But he ended his essay. Towards the end, he said, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. We should be grateful for it. Interesting. He used the word miracle. Miracle, miracle. When you think of miracles, what do you usually think about? You think about some of God. You think about divinity. You think of the supernatural. So he said, it's the miracle of the appropriateness of the language. When you think of language, you think of order, you think of reason, you think of something structured. So the miracle of the language of mathematics is a wonderful gift. Look at this language here, a gift. A gift implies what? A gift giver. You have a gift, somebody had to give it to you. And if you think pure chance, pure luck of the draw, go right ahead. You got plenty of company. But if you're going to be a little more logical, a little more reasonable, logic and reason alone would tell you that the giver of this gift is God, the creator of the heavens and the earth.